Welcome back to Topics in Statics. This time we're going to talk about structural analysis, in particular the method of joints. To begin with, the first types of structures we're going to talk about are trusses. A truss is a structure that's composed of slender members joined together at their endpoints. A plane truss, which is what we're going to talk about to begin with, all the members lie in a single plane. And if the loading also acts in the same plane, then the entire analysis for this structure is going to be two-dimensional, which is a good thing. A simple truss, which is what we're going to talk about, is one made up of triangles, and that produces a rigid structure. The big assumption is that the members are joined together by smooth pins, and so all the loadings are applied at the joints. So when I want to load the truss up, I applied an external load only at the joints, not in the middle of the member. The consequence is that each truss member will then act as a two-force member. In other words, there's only two forces acting on it at opposite ends. And so those forces either point away from each other, they either pull on the member, in which case the member's in tension, or they point towards each other, and we refer to the member as being in compression. The method of joints is just applying our equations of equilibrium. Because the truss is in equilibrium, that means each joint is also in equilibrium. Because all the members are two-force members, each joint is subjected to forces which are not only coplanar, they're also concurrent. They're concurrent at that point. That means there's no moments in this, right? That I've eliminated the moment equation. There's no moments about that point. So the equations for equilibrium are simply sum of the forces x equals 0, sum of the forces y equals 0. Now, because I've only got two equations, that means any joint that I want to analyze, I can have at most two unknowns, because I can't solve for more than that. Choosing the correct sense for the forces. Which way do the forces point? Do they point left, or do they point to the right? Do they point up, or do they point down? That's what I mean by the sense. A lot of times you can figure it out before you draw your picture. If it's too hard to figure out, you can always just assume that all these unknown forces are pulling on the joint. Then if you end up with a negative answer for one of those, it tells you, oh, you drew the arrow the wrong direction. It should point into the joint, not out of the joint. To give you an example, let's consider this simple little truss over here on the right. And we look at joint B. Here's joint B. And there's a force, an applied load pointing to the right. This is the force applied to it. Now there's two other forces which are along the beam. So there's going to be one pointing up and down between points A and B, and another one that points down and to the right, which is, sorry, I don't know which, I'm trying to figure out which direction it points. It runs down and to the right, and that's going to be so now if this load is applied and it points to the right, I know it points to the right. Well, the only other force that produces any x direction is this FBC. So it has to point to the left, which means it points into the joint. And if that one's pointing into the joint, it produces a y direction, a positive y, and so I need something pointing down in the y. So that's what I mean by figuring out the sense. I know those are the correct senses for those forces. Like I say, if you don't want to go through all of that, just make them all point out of the joint, and any that show up as negative means they're in the opposite sense. Sometimes there are joints in a truss, or there are members in a truss, which don't support a load, that there is no tension or compression in this beam. And the reason is that the truss is designed to handle all kinds of different loads. And for the specific load you're looking at, there may not need to be any loading within that beam. There's two basic situations I look for. If a joint has only two non-collinear members and there's no external load or support at the reaction. So in other words, I've got a truss. I don't know what this truss looks like. I don't know why I have a truss that looks like this. Maybe that's a horrible example. Scratch all that. If I have two non-collinear members and there's no external load, so let's back up. That means I've got a joint that looks like this. Right? If there's no external load at that at that joint, then each of those members has to be a zero force member, because there's no way to make those two add up to zero. If you have a joint where there's three things coming into it, but two of them are collinear, so I've got two going this way and one going this way. If there's no external load applied at that joint, then that one pointing up is going to be zero. Why? Because the other two can be equal to each other. They have to be equal to each other. So an example. If I look at joint D up here, at joint D, there's a force. I'm just going to make both of these point out. Well, the only way those two can be equal, or the only way that joint can be in equilibrium, is if those two forces are equal to zero. And so both of those are zero force members. So this is a zero force member and this is a zero force member. And the reason that's true is just because of the loading. If it was a different loading, that may not be true anymore. Another example, we can look at joints C and D. At joint D, here's joint D. I can all point out there's one pointing this way, one pointing this way, one pointing this way. Well, if FED is equal to FCD, the only way that can be in equilibrium is if that one is zero. Right? If I look at joint C, here I've got one pointing this way, one pointing this way, one pointing this way. The only way that can be in equilibrium is that one's zero. It can simplify your life if you learn to look at that early in the problem and recognize that, oh, this one's zero. I don't have to calculate anymore. That's nice. I like not calculating. So my basic procedure for the method of joints. I draw the free body diagram of a joint with at least one known force and at most two unknown. I determine the sense of the forces. Not until I've done all of that do I draw the X and Y axes. Then I solve for whatever I need to solve for. I use those results, I analyze another joint, and I continue until I'm done analyzing the truss. So let's work a problem. Determine the force in each member of the truss. So I've got a whole list. A lot of times it helps to go ahead and make a list of what all am I looking for. So let's do that. So I need to find FAB, FAD, FBC, FBD, and FCD. There's 5 forces I'm looking for. So where do we start? First, let's look at the truss. Are there any zero force members? Well, the only joint that's important is to look at B. If I look at B, I can tell that the force BD has to be equal to 0. That AB has to be equal to BC, and that means BD has to be 0. So we're 1/5 of the way done and we haven't calculated anything. That's great. So now let's look at joint D. Joint D, here's joint D. There's a force this way. This is and then there's two forces, one that way, one that way. Which way do they point? Well, one's going to point left, right, and one's going to point up, down. So which one's which? Don't know. Let's make them both point out. Don't know which one's going to point up and which one's going to point down. So what are these? This is FAD, and this is FCD. So now let's do the sum of the forces in the x direction. Well, we need a coordinate system. Let's put a coordinate system in here. And we'll just pick the usual coordinate system. And we know that this is 45 degrees and this is 45 degrees. So now we do the sum of the forces x equals 0. So I get minus 450 plus FCD times the cosine of 45 degrees minus FAD times the cosine of 45 degrees. Then we do the sum of the forces in the y direction equals 0. We get minus FCD sine 45 minus FAD sine 45 equals 0. And then we solve. And if we solve all this, what we find is FCD is 318 pounds. And FAD is minus 318 pounds. That minus sign tells me that the arrow on FAD is the wrong direction. Right? So FCD, I'm going to put this in my list. FCD is 318 pounds. And because that's pulling on that joint, that means that member is in tension. FAD is also 318 pounds, but this member is in compression. So armed with all that knowledge, we move down here. Now we move to another joint. This is joint A. At joint A, I've got a support reaction. So I've got a force pointing up here. This is a Y. That's from that roller support. It only produces a force in the Y direction. In addition, I've got this force and this force. So FAD, the beam is in compression. Well, let's just draw it this way. This is FAD. We're going to leave it this way. I'm going to make this one point this way. This is FAB. Right? I already know that from the previous page, FAD is minus 318 pounds. Why is it minus? It's still minus because I've drawn it the same sense as I had before. that it's pulling on the joint. In reality, it's pushing on the joint. So from that, I can do the sum of the forces in the x direction equals 0, which tells me that FAB plus negative 318 pounds times the cosine of 45 degrees equals 0. So for FAB, that's 225 pounds. So we go back to our list. FAB is going to be 225 pounds. That's in tension because it's pulling on the beam. And since we already figured out that BD is 0, FBC has to be equal to FAB. So this is also equal to 225 pounds. And it's in tension. And we're done. And that's how you work a method of joints problems. You solve one, use that to move to the next one, keep going until you've done everything you need to do. Next time we'll talk about another method of analyzing trusses called the method of sections.